Okay, good afternoon, everyone. Thank you very much for being here and for following us through YouTube in this another seminar of the Astronomy Department seminars. Today we are going to have a joint seminar and we are going to have two speakers. First, we are going to have Jura Borissova currently for the Universidad de Valparaiso. And after, no, sorry, I mixed up. It's okay. It's okay. First is going to be Jura Borissova, and followed by Radosnit Kurtev. Radostim. Kurtev, sorry. And they have similar trajectories. They made their studies, undergraduate studies and PhD at Sofia in Bulgaria. And then after a while, they visited the University of Valparaiso in Chile, and they stayed there, and they are both full professors there. And first, we are going to start with a seminar near-infrared variability and spectroscopy, followed by optical and near-infrared photometry of young stellar objects candidates. And we are receiving questions after both parts of the seminar, and the same for the questions in the YouTube if you are following us online. Okay, so please do that.
Thank you.
You're welcome.
Thank you, all of them, to be here in this very short seminar. First, I will speak a little bit of young stellar object in Carina star-forming region. So this is well-known picture of the James Webb, and we have some picture above in the VVX infrared survey, which is not comparable, of course, but you can see that VVV, which is from the ground, is more or less usable for the study of stellar populations. So Carina is a star-forming region, relatively close, 2.5 kiloparsec, and this is one of the most active massive regions of star formation in our clouds. And this region is studied a lot, more than 300 studies in the region, but still we can study some specific things connected with this star forming region. And we concentrate on the young stellar object. Here you have some papers, previous studies, that we use specifically connected with young stellar object. As I told you, there are more than 300 studies in this, but this is the recent work that are dealing with young stellar object, and this is the map from 2023 using Gaia data release to put the map of the young stellar objects which are detected in the sky. So why we study this? Our goal initially, we studied this project 5 years ago, was to prepare some kind of training set, because machine learning, artificial intelligence, this is the future. But to work well, we need to have some background and compare. So our goal was to select young stellar object, some kind of statistically significant sample, which will very carefully select the object we think and prove that are young stellar object. How? We combine the variability using VVV Higgs. This is VISTA Variables extended survey, maybe you hear about this, and H-band photometry for Sloan apogee 2. This is middle resolution spectroscopy, and we are going to combine K-band variability with some kind of features which are connected with activity. And these are emission-lined high accretion, which are tracers of high accretion rate. And another tracer of the high of young stellar objects is variability. Almost 90% of the young stellar objects show some kind of variability. So the Apogee 2, as I told you, we started this 5 years ago, a little bit delay connected with, I don't know, pandemic and such things. So this is multi-object near infrared spectrum of 300 fibers. Not all of them are objects. We have 50 for sky, 25 for telluric, some kind. But in general, you can put 230, 240 objects, real objects on this. Well, in 2020, it was a physical, very heavy plates with aluminum. Now, with Sloan data release 5, they change, and we have multi-fiber system. So in 2020, we observed approximately 700 objects, which are previously selected, both with variability and not showing variability. And the preliminary reduction was done using data release 17, the pipeline which is giving preliminary reduction. You know, telluric, sky, and all these things which are necessary. And we are observing in H band, only in this wavelength range, the resolution in 2500 thousandths. So, when we have the reduced preliminary reduction of these 760 specters, we think what to do with them. First of all, this is not a huge sample. We are not speaking of several million objects, which is the situation now. There are only 700. This is one kind. On another hand, expecting this spectra by eye or one by one, this is a huge amount of time. So we decide to use the simplest unsupervised method, and this is the K-mean. Because of the size of the sample, not too small, not too big. So we try this unsupervised using some spectra. Here you have this spectra, some examples of the spectra. And the first was to clean this noise connected with the instrument. You cannot reduce them. You have to remove them in some kind of algorithm. So first we clean the spectrum. The second one we're choosing for a line, which is representative of the activity. And this is the bracket 11 because we are in the H band. We also try to use bracket 13, which is also good indicator, but bracket 11 is much stable. And bracket 12, it is not possible to use because in that time, this spectrograph has 3 parts of the spectrum. And the bracket 12 is exactamente in the gap. Exactly in the gap. So, running this unsupervised classification method, we run this many times. So, finally, it's conclude with 8 clusters which offer the best partition. Then here you have some picture of these 8 clusters named from 0 to 7. And the partition of these clusters was in some way done. So, because this is the semi-supervised, unsupervised method, we have to verify and validate this partition of 8 clusters. So we perform visual inspection of every spectrum that we classify in one of these clusters. And we found the sum of the clusters. For example, here you have cluster 3, cluster 2, cluster 6, and cluster 7. For example, cluster 7 contains only 2 objects. Why? Because there are huge emission and it is superimposed with another line. Or in most of the cases which we have here, which are not well classified, contain, for example, one of them contains 0 signal, so the algorithm don't know what to do. But finally, after visual classification and removing, here, for example, you can see another example. It's so shift because of high radial velocity. So it's not possible for the automatic unsupervised method to classify them. Here you have another, this is the sum per signi per profile, and here you have very low signal to noise. So finally, we expect all these 760 spectra and separate them in 3 clusters. One is bracket 11 in emission, another in bracket 11 in absorption. In the third group is all these spectra that we cannot classify, either automatically, either visual inspection. So here you have the confusion matrix, which is for this simple method completely well. 68, 69, 79 of the third group, of course. Yeah. So, also from this unclassified spectra, we compare with literature catalog. And if we find that we have the same object with the literature, we reclassify them as emission or absorption line object. And the third verification of our classification was using the variability. In VVV-Higgs, we have 6 tiles. We perform the PSF photometry and variability search using various methods. And all the stars in this group 3 with uncertain classification that if they show some variability, they reclassify like young stellar objects, because variability is one of the tracers. Here you have some example, and Rudy will speak more about this. When we have this sample, we also check for binary stars and some other stuff to classify, to fine-tune the classification. Color magnitude diagrams, one is from VVV-X. Here you have different groups, emission lines, young stellar objects, absorptions, and our literature of variable stars. And here is the Gaia. Gaia, the objects are not so much, because this is the infrared clusters, they are variable, so Gaia didn't detect them well. But in general, in K, as you can see, they are bright. So you can see that here you have more or less consistent distribution of the spectral classification. Main sequence are mainly absorption stars, and here you have some emission line stars. Some physical parameters. Star house is a valued added catalog which come from Apuche. And the Gaia data release 3, you can see that most of our objects, young stellar objects, are low mass stars, and we have only 8 stars which are around 10 solar masses. And we didn't find any statistically significant connection between mass and spatial position. The same for temperature distribution. Most of the stars are in the range when the young stellar objects are expected. The Gaia, as I said, have less objects, and also the parameters are with higher deviation, again for the reason that these are infrared objects and are variable. Metallicity, about solar metallicity. So this is the picture of physical parameters. Also membership probability, we find 2.25 distance using young stellar object, which is very close to the sample of OB stars, which are from Isogaya survey. So we are fine. Finally, we have 652 objects which are trustable young stellar objects. Some of them are B stars or but Herbig R or something like this, but they are young. Current work, we are working now comparing the age and the mass distribution of all B young stellar objects and Carina. And we can see that there is no much coincidence between O, B, and young stellar object stars. Also, we are looking for correlation between H alpha and bracket 11. And we have some correlation, which is logical because each H alpha shows some emissions. The same is with bracket gamma, and here we have some exceptions. No H alpha, a huge, large bracket gamma values, but we are still working on this explanation. This is the master degree thesis of Javier Oces. Future work on Carina, we are going to include this in a recently starting survey, KMOS, with KMOS, 22 fibers, we can use the spectra, and optical variability from Vera Rubin. And now a few words of now this new project, not new, but this is one survey which is starting next year from March. This is 2-year survey, 140 hours of the survey. KMOS band photometry, or H plus K, low resolution, 4000 in K. You can go for 2000 also. And one of the topic is massive young stellar cluster. So we are trying to select the objects which are possibly from one clot. And we selected here all the clusters from Bika et al., which has many objects, but most of them are not followed spectroscopically. So we are trying to select the objects which are young, massive infrared star clusters. To be, again, to create some trustable catalog of the clusters, and in this way trace the recent star formation in our galaxy. Here you have some example of VVV clusters and Bika and all clusters. And here, from this color magnitude diagrams, we selected the object from the KMOS configuration to obtain the spectra with K band. So this is just started. We still have time by the end of the year. So if somebody is interested to include some object, no guarantee, but worth to try, please contact me. Thank you.
Thank you.
Yeah.
Perfect.
What? one of the size.
Put it in the pocket.
Okay.
Are you hearing me? Oh, yeah. Okay. So I will continue with the photometry. First, I will continue the objects Jura mentioned. So this is worked together with Jura, of course, and with our colleague Jen and some of our students. So first, I will talk about the near KS band photometry of Carina and the variability of YSOs at Carina, and they will give you some information about the results of the photometric study of young stellar objects using Alersi broker and ZTF. So let me repeat about the Carina. So our students, former student Nicolas Medina, made a huge photometry about more than 1 million objects of these 6 tiles. Study variability of these objects and found 606 variable objects, possible young stellar ones. The cut of this photometry was 0.2 magnitudes in KS. So everything which is more variable than 0.2 was accepted as a variable object. So we generated this catalog, including also the data from spectroscopy, from apogee, so the mass, the effective temperature, and many photometric points about this one. So the KS mean magnitudes, delta amplitudes, variances, and skewness, and kurtosis, and so on. So everybody of you can use the catalog because it is machine readable catalog. So we have problems, and one of the problems is that we have not too many epochs. So some of the objects are 10 epochs, 20 epochs of variability, and also some of the objects are very bright. So if you have less than 10 observations, we can almost tell nothing about the statistics. If you have about 20 to 25, we can give some basic things, so some kind of amplitudes or periods, and so on and so forth. But if you have if you have more than 30, already can give some statistical indices with more reliability. So we divided the objects in reliable and unreliable flags, with unreliable flags, and reliable are more than 30 observations, and KS band more than 11.5. So here in this picture, you can see the all data with red, with green are the reliable, and with blue are periodic ones. So we constructed many diagrams. I will show you the most interesting one. And this is the amplitude versus mean magnitude. With red are all the objects again. So you can see that this one, which are brighter, show very high amplitudes. But this is not real. These are actually saturated or nonlinear objects. The PSF photometry can reduce a bit this, but not do everything. So at the end, we decided that, as I said, remove these ones. And we see very nice relation between the amplitude of the objects and the mean magnitude. We see that the more brighter one, as Jura said, there are not too massive in our samples, but there are some which has a masses about 4 or 5. So the less massive ones, less brighter ones, actually show less variability and less amplitude. And this one should be seen if you're talking about the young stellar objects, because the lower amplitude ones are more variable. I will explain in a minute why. And here I'm showing you some examples. So these are some eclipsing binary candidates with the period of H1. These are some quasi-periodic examples with a bit higher periods. And these are some probably rotationally modulated variability because of spots, bright or dark ones. With, of course, with less periods, and this should be period of rotation of the stars. So this is some kind of details about the Carina object. So let me explain why we should expect more variability when we're talking about the less massive ones. The less massive Young's theorem. Oh, this is the. Oh, sorry. This is the common picture of an Young's theorem object with low massive one. So this is the central star. This is a disk. Always there is a disk because of conservation of the angular momentum, of course. So the gas and dust is settled on disk. And through the magnetic field, the disk inside part of the disk is truncated and the material is falling on the surface of star. And this is the mechanism of growing of mass of the star. And in low mass stars, we have very strong magnetic fields because low massive stars are very convective, and this is generated bipolar magnetic field. With the higher mass stars, we have no such strong magnetic fields because the higher mass stars are functioning with the radiative move of the flux of the energy. So they are not generated so higher magnetic fields, and probably the material from the disk are falling directly to the star and producing not so high variable events. We can observe different part of the disk of the Young's theorem object actually in different wavelengths. In the inside part, we have a high temperature layers of the star, so this is ultraviolet and X-ray also. The inside part of the disk is emitting in the infrared and in the optical, and outside, of course, in the radio and in the middle infrared also. Why am I showing this in so details? Because the Young's theorem object is a very active thing, and if it's very active object, should expect variability. There are many kinds of variability of this object, and the reasons of this variability are different. So with here, with the amplitude versus full scale, full cycle event time scale in days, you can see with blue accretion-related events, with purple routine variability connected with the rotation, with red extinction-related behavior, and with green binary-related phenomena. It means that we're talking about the binary star, or eventually of some point of some part of the disk which is rotating around the star. This kind of events here, they are very rare. So outbursts and bursts, in general, they are very rare. You can see them once per century in some objects. Some colleagues say that once for a lifetime of the star. And with our study, actually, we are using this part of the time domain. So, few words about the types of Young's theorem objects. We have 4 types of Young's theorem objects. The first ones, class 0 and class 1, are actually protostars. These one can be observed only in the radio or far infrared. You can see the spectral energy distribution here. So actually, we cannot see nothing before the near infrared. And class 2 and class 3, we can observe them in the opticals and in the near infrared. So these are actually the protostars. These are actually the pre-main sequence stars. I'm sorry. So these are protostars and main sequence stars. So we will use some indices in order to characterize the variability of these objects, and this one is the normalized peak-to-peak variability matrix. This is actually the maximum minus minimum magnitude versus maximum plus minimum magnitude. The 5 sigma outliers are out, and finally we have objects with nu greater than the 15 percentile. So the blue ones. The other one is quasi-periodicity index. In order to have a good quasi-periodicity index, we should have a good period of the star. So we are using Coulomb's-Cargol usually in order to find the period. So what we are doing is finding the period of the star, subtracting the train, the main one, and finally studying the residuals. So the Q index is the standard deviation of residuals minus errors of the photometry versus standard deviation of the initial light curve minus the errors. And the Q, we have it from 0 if you have a perfect periodicity, which means that the standard deviation of residuals is something near to the errors of the observations, it should be something near to 0. And if you have a fully stochastic behavior, we should have some Q around 1. Yes. Because this one should be, the residuals actually should be almost equal to the standard deviation of the light curve. And the other parameter is the flux asymmetry, which is the difference between the mean between the 10% superior and 10% inferior of the magnitudes of the points, minus the median magnitude of the point. This is proposed by Cody using data from Korot and K2. So if you have a bursting behavior here, we should have very negative index because the median magnitude is lower than the mean of the 10%, so the value is higher and the index is negative, and we should have 1 if we have a case of dipping behavior. So we can use combination of this one and Q and M in order to characterize the stars. Here you can see the real examples. This is the bursting and dipping. And this is the periodic, and this is full stochastic behavior. So using these two, we can separate 9 different classes of variability of Young-Stellar objects. And this is burst periodic, quasi-periodic burst, burst stochastic, symmetric periodic, quasi-periodic symmetric, symmetric stochastic, deeper periodic, quasi-periodic deeper, and deeper stochastic. And okay, we have the method. So now we should have the data. There are many data. Jura showed you that there is a huge catalog of Martins and collaborators. But we decided to have another approach. We with Jura are members of the LRC team. This is one of the 6 official brokers of LSST. LRC using the stream, so it was, how to say, educated using the ZTF data. ZTF, probably you know that it's the 2-meter telescope, 3K transient facility. It's in Mount Palomar. It has a huge camera. is doing almost the same as will do the LSST or variability. So we use a LSS broker. It has a balanced random forest mechanism in order to search for variability and to classify the objects. So we relax this one, and find many objects with the LSS classified as Young-Stellar objects. I missed, unfortunately, I missed the the pointer. Okay, I will use this one only for the public. So we cross-match this. Okay, we add 76,000 objects found in the SIMBAD. Add this to 326,000 of LSS. Cross-identify with Gaia. As LSS and Gaia are optical and are the same filters, we have almost all presented in Gaia. So we use Gaia also and restricted our searches in our, let's say, this pilot study into the 2 kiloparsecs. And we have 52 variable objects, so YSO candidates. We know perfectly that there are many contaminators in this one because we relaxed the parameters. But we can use, okay, the main contaminators are the long period variables. And here you can see the light curves with LSS of the 2 or 3 examples of the Young-Stellar objects. This one is the folded light curve, and these are the normal light curves. And here is the behavior of the LPV star. So if you look at the light curve, there are not too many differences. So this is the whole sample. The core magnitude diagram using Gaia. This is absolute magnitude versus the Gaia core. With red are all objects, and with this green one are the Young-Stellar ones. How are they selected? They are selected also with the help of the middle infrared observations with WISE. So here with WISE we can select this one. This is the zone of the Young-Stellar objects. These are all the LPVs in some long period variables. So they are much more numerous. And this is the other core diagram using only W1, W2, and W3 cores. And we plot this in the galactic plane, and we have very nice coincidence with the centers of the known star-forming region. So we choose with my undergraduate student some star-forming regions around S155, IC1396. This is a cluster, so the region around the cluster. This is also the open cluster, so the region around the open cluster. And apply the QM technique. But, well, this is the selection of the object using Gaia, the proper motions and the parallaxes in order to be sure that we have the objects from the cluster and from the zone. And here you can see the QM plots of the different ones. What we can tell immediately is that the zone of the symmetric quasi-periodic and symmetric stochastic is the most populated one. The size of the symbol is correlated with the amplitude of the object. So bigger amplitude, bigger symbol. And this is the M36. So we can construct also this kind of histograms or classification plots, and to see how is presented each of these classes So the sum of this one is 100%. So you can see that there are differences between these ones. This is the work of Lynn Hillenbrand over the Pelican Nebula in North America. And definitely you can see that, as I said, the quasi-periodic symmetric and stochastic symmetric are well presented in all these diagrams. In order to be, how to say, to be absolutely sure how it is working, we choose very well and very good studied region, and this is Orion. And use the data from the paper of Marina Kunkel and collaborators, and they constructed 6-dimensional picture of the Orion using radial velocity from apogee and proper motions and distances from Gaia. So there are subregions in Orion. This is Orion A, B, C, D, and Lambda Orion. They are presented in different colors here. You can see this. So this is the distribution over the sky and the positions of the stars in Orion. This is the velocity of each subregion, and this is the parallaxes. You can see the parallaxes and the distances also here. So this one and this one is the same. And we made the QM plots of different regions of Orion. Some of the regions are more populated, some of the regions are less populated, of course. And we constructed, this is Lambda Ori, and we constructed the QM diagrams. But before this, it's good to tell something about the periodic ones. We have only 4% of the stars with a good period, strongly periodic, which is some kind of less, some kind of low value, but from other point is acceptable, because you know that the stochastic behavior is the most prominent for the youngster object. Most of the stars are showing less period, less than five days, so probably is connected with the rotation, and some of the longer periods are probably connected with binarity. And here is the result. And the result is a bit interesting, a bit speculative, need more confirmation. But in general, we see that Ori Lambda and Ori B, which are much younger than Ori C and D, in this one, quasi-periodic dippers and deeper stochastic are much well presented than the other ones. And the most younger one, which is Orion A, which is mixed also with some kind of older population, the quasi-periodic bursters and burster stochastic are well presented. So we should expect some more activity in the younger regions. So this is some kind of summary. We use only G filter, not R filter. So we should include R filter also in our analysis. We should analyze the colors in order to distinguish between extinction and the real change of the colors. And this is the work of my PhD student, Vania Rodriguez, who will do this in a massive way. So our idea is actually to, at the end, to construct a reliable sample of all stars, young stellar objects, and to use QM in order to classify them, and to see if there are some differences between the star formation rates of the region, some ages of the region, and so on and so forth. And why we are doing this? Everything is pointing to the Vera Rubin. Vera Rubin will be very good for this. So, well, somebody say, oh, this is an exceptional platform. Yes, it will be really nice because with very deep photometry, with regular photometry, but unfortunately not so with not so frequent observations. So with ZTF we have every day one observation, and with the LSST we will have every 3 to 4 days one observation. So if you like to study in detail some of the regions, probably we'll do some additional much higher cadence surveys. There are some ideas to do this with LSST. It depends, you know, of the committees. But probably in the next semester we will propose to do this with the Chilean facilities, with smaller telescope, with the higher integration time, and we'll reach probably the same or similar limiting magnitude. Okay, so obrigado. Thanks, gracias y благодаря.
Okay, thank you very much. Thank you very much to both speakers. And we are open for questions.
So we are fitting 45 minutes, which is great.
Yeah. We have time for questions.
Hello. Thank you so much for the presentation. It was very, very good. I have 2 questions, actually. The first one, as you said, when you have all the methodology set, you can choose different data sets. And I was wondering what you guys think about using the new WISE, because it is in the mid-infrared. Maybe you can see like more cold stars.
Yes, the WISE is substantial in this.
Yeah, because in my group we're starting to think to use the near Earth object WISE. It has like more than 10 years of observation, and I was thinking about if that could be like helpful in this situation as well.
Okay, I have no time, and it was not in the topic, but we have a colleague, Jengo, who is working on the individual objects, and then he's using the WISE in order to see and to compare the variability in the middle infrared with the variability in the near infrared using the VV survey, the data from the VV survey. So the VV is also 10 years, with the span 10 years, and the WISE is almost the same. So you can see very, very nice result, and comparing the amplitudes in the middle infrared, as if we come back on the disk, you see that the different part of the disk are emitting in the different wavelengths. So you can compare and to have some ideas about the structure of the disk.
Perfect, thank you. And just one more quick question. I was wondering, when you showed the graph of the period and the type of variability, I was wondering how can you certainly distinguish between the hotspot variability and the eclipsing binary, because they have some kind of overlap, and you showed...
they have some overlap. Yeah, they have some kind of overlap in the form of the light curve.
Okay.
So the spots should be much more regular, and the binarity one, you should have, you know, there's some kind of plateau and minimum, some kind of plateau and minimum. So you can see the morphology of the light curve in order to start to try to distinguish between these 2 events.
Okay, thank you.
And you have radial velocity, such kind of stuff. It's better, but
Thank you for both talks. I'm not of this area, I don't work with stars, so I take the opportunity to learn something. Are these objects already in the main sequence, or they are going to the main sequence?
It depends. If you are talking of the protostars, they are far away from the main sequence, and they are observed only in the middle infrared and the radio and with ALMA. But if you're talking the premium superstars, they are just above we are talking about the classical Tauri stars or weak Tauri stars or BE stars, Epicaro BE stars or something like this. So these are along a bit above the main sequence and along the main sequence, depending on their mass.
Almost there.
Almost there.
Okay.
So they are candidates for going to the main sequence.
Okay, thank you.
More questions?
Oops. Thank you for the both talks. In your first talk, you mentioned the Star Horse, which is our code actually, and I was thinking, I didn't understand exactly how is Star Horse useful, because Star Horse assumes nobody's varying.
In data release 17 of Gaia, we have 3 value-added catalogs. One is Starhouse, another one is Neuronet, and then in the third one I don't remember. We compare 3 of them.
But what?
And physical parameters, temperature, mass, gravity, all these things. And compares, and Gaia. So the Gaia is worse. They are obtaining very huge variability, outliers, blah, blah, because maybe Gaia data release 4 will be better. But Gaia data release 3 is not working very well for young stellar object, this kind of young stellar object. So we compare these 3 value-added catalogs. I know that they are not taking in consideration prime sequence stars. The star house is performing better than other 3.
No, I would like to, yeah, this is good news. I would like to understand how are we performing better, but we have 2 catalogs, right? One is or several, but one is this one that was released with Apogee, right? And it used a lot of photometric bands plus the Gaia information to give some stellar parameters, right?
Yeah.
So maybe it's working because for subsample parallax is excellent, or I don't know.
Maybe.
But the thing that Star Horse can do is to give you a good idea of the extinction. But if the thing is varying, then I don't know.
I have some masses, I have some temperature, and I have some metallicity. I didn't trust the ages.
No,
because they are using isochrone for evolved stars.
Exactly, yeah.
There is no prime sequence here. So I am not using ages.
Nor masses.
I am using only extinction.
Okay.
I am using the parallax comparing with distance from Gaia, because there is a difference between Star House and Gaia.
Star Horse,
sorry.
The difference is exactly into this treatment of the extinction, because we join the Gaia data with more photometry, and therefore we gain into precision into the extinction. Now I'm saying this because meanwhile we prepared another catalog, which is a machine learning catalog that can pick up other regions, and maybe that one is interesting.
I know, but this catalog, the new one that you prepare, is not including Apogee 2 in Las Campanas. Only the infrared spectroscopy in United States. I checked carefully. This is data release 19.
Oh yeah, no. I'm sure. Yeah, the ones of Apogee. I'm talking about. Forget about Apogee. I'm talking about another Star Horse. But I can show you. It's a Galatian et al. But maybe it's useful. I can. You can contact us actually, and to see if we can help in any case.
Yeah. Thank you.
Thank you.
Okay. So do we have more questions? Yeah. Okay. Thank you.
Sorry. Hello. I'm sorry for both your presentations. I have a question for the first one as well. Do you try to use other forms to other than k-means? Because I know that that is better or more sophisticated ways to determine a cluster. I didn't understand well why you choose the simplest. Okay.
We have 700 stars in not 7 million, but I'll give you. There is one work on which include our spectra inside the collaboration Sloan. And this work is using a random forest or something like this, which is more sophisticated. I'm not objecting this. The problem is that I have to spend time to educate the algorithm in order to select correctly. When we compare our sample, which I confirm by I and other criterion, with this sample of Campbell et al., we have only 38 objects in common. Why? Because they are training the set using some samples which are not exactly young stellar objects. These are in general emission line stars. And the emission line stars can be O or B. So we are concentrated on the young stellar object. And for this reason, we use the simple one, but validate this.
Maybe the result of the KMOS survey where we have more.
Yeah, maybe with KMOS we will have more certainty, let's say.
Okay, let's thanks again the speakers. Thank you very much.
Thank you.
Thank you, thank you.
It's a pleasure to be here for the first time, but maybe we will come back.
Yes, sure. And we invite everyone to keep on discussing during coffee
and
break.
we are inviting you to come in Valparaiso, and,
Yes.
and if any of you have some ideas, we can do something together in common.
Okay, thank you very much.
Yeah. To enjoy the Chilean facilities.